so I had to resume. That's what it was. Oh, that's scary. Well, we missed a lot of it. Anyways, so now I'm going to go back to where we were. Sorry about that. All right, just to recap, because evidently I had my recording paused and thought I had actually turned it back on, but I must not have hit the button. Sometimes when you hit a button on a window that's not active, you have to actually hit it twice to get it to become active and to hit the button. So I think that's what I ended up not doing. So just to refresh yourself, what you're looking at is the solution of this problem, example 1. I first did reduce the resistances of the 5 ohm and the 6 ohm resistor that are in parallel. I called that R5, 6, and found that was 2.727. That's what the lightest dashed line is replacing. And then that 2.727 ohm resistor was in series with the 4 ohm resistor. So I just added those, and that made the slightly darker outline be replaced with 6.727 ohms. And then that 6.727 ohms was in parallel with the 7 ohm resistor. So I used the parallel formula to do 1 over R. Notice I wrote it as 4, 5, 6, 7. And that's the dot dash line around it. That one resulted in basically a 3.430 ohm resistor. And then, of course, that was in series with a 8 and a 0.5. That's where we are now. I just used arguments to make sure everybody understood that the total current, the current leaving the battery, if you will, is the current through the 8 ohm resistor and through the 0.5 ohm resistor. And now I'm working using Ohm's law to calculate the voltage across the 0.5 ohm resistor, which I'm going to call V 0.5. So that's the V 0.5. That's equal to I 0.5, which we know is 1.006 amps times 0.50 ohms. And what we end up having, of course, is 3 sig figs times 2 sig figs just gives us 2 sig figs. So this answer is going to be 0.50. If I carry one extra digit, it would be 5003. So that's not very impressive either way. So I'm just going to say 0.500 volts is the voltage drop across the internal resistance 0.5. So V 0.5 is that quantity. Now I can use my little bubble again to establish what the actual voltage is on the left side of that resistor. So you can see the voltage dropped by 0.5. So right here, it's going to be 11.5 volts. Does that make sense? So now I can also say that's about the same as the voltage right here, and that's about the same as the voltage right there. Okay. Now, if I were to calculate the voltage across the 8 ohm resistor, then I could get that voltage with this dot right here. Everybody see the red dot I just drew at the top of the 8 ohm resistor? And that's going to be the same as this point, and this point, which could help us a lot. So I'm going to do that now. I know V8 not the drink, is equal to, again, I8, which is the total current, amps, times 8.00, omega, ohms in other words. So that's clearly going to be 8.0, and then 0 times 6 gives us 48, so that'd be 48 here. And that is 8.048 amps. I'm multiplying 3 sig figs times 3 sig figs, so that 8 on the end is not a significant figure. But like I said, I'll keep this number. And that tells us, in fact, that the voltage, which was 0 at the bottom end of the 8, is going to be higher by 8.048 volts at the other end. So I'm going to say 8.048 volts is the voltage right here. But that's also, as I said, the voltage here, the voltage here, and the voltage here. Again, it will be a little bit lower, or excuse me, a little bit higher for this case because the wire has some resistance. So it actually have to, in order for current to flow from those three dots to the 8.048 volts, it has to be a little bit higher voltage than 8.048. So hopefully that makes sense to you guys. But with that, we can automatically see exactly what the voltage across the 7 ohm resistor is. Clearly, it is 11.5 minus 8.048. So we can use that right now to calculate. I'm going to go ahead and label this 8.048 as V8 and box it off so we'll have it. And now I can calculate V7. And of course, there's other ways to do this too, but in this case, I'm just going to grab it while I got it. So V7 is going to be 11. Whoa, nearly. V7 is going to be 11.50 volts minus 8.048 volts. And when I do that, just to be careful because I'm prone to making arithmetic mistakes, 11.5 minus 8.048 gives me 3.452. And that would be equal to V7. And like I said, I like to have the name right next to the number, so that's why I had to write it there. So we now know the voltage across that. I can use that, in fact, to get the voltage going through the 7 ohm resistor, and that will work out really nicely. So I'm doing it a little different than I did last time. Remember, I said, wait a second, there's a real easy way to do this by using these voltages, but I don't want to do that. I want to show you the hard way. Well, this time I'm going to go ahead and use the easy way. And what I'm going to calculate is the current through the 7 ohm resistor, which we call I7. And that's going to be the voltage across the 7 ohm resistor divided by 7.00 ohms. That's going to be 3.452. And of course, that 2 is not a sig fig. So that's 3.452 volts divided by 7.00 ohms. And that gives me 0.4931, 0.4931 amps. Again, that's one extra sig fig, and this is I7, the current through the 7 ohm resistor. Any questions on that one? Now, remember what we have is a 1.006 ohm, or excuse me, amp current coming in that goes up here like this, and then it hangs a right, and then it breaks off into two, whereas this current right here is 0.4931 amps. So this one right here, we should be able to calculate just from an idea of conservation of charge. Now that's the current that actually goes into the 4 ohm resistor. So I'm going to write that as I4. Okay. What we see is 1.006 amps is equal to 0.4931 amps plus I4. So I can use that to find I4, and what I'll get is I4 is equal to, notice I'm just going to take the 1.006 and I'm going to subtract from it the 0.493 that I just got. That's going to give me 0.5129. 0.5129, one extra sig fig again, amps. So now I know how much current is going through the 4 ohm resistor, and that's kind of helpful. And I know the one through the 7 ohm resistor. Not only that, now that I know the one through the 4 ohm resistor, I can find the voltage across the 4 ohm resistor, and that would give me the next bubble between the 4 and the 5 and 6. And of course, that means that's the voltage at the right edge of the 4 ohm resistor, but it's also essentially the same as the voltage at the left end of the 5 and 6 ohm resistor. Does that make sense to everyone? John, you getting it? Does that make sense? Looks like you're looking intently, so I assumed that meant you were getting it, but I was afraid it might have been some confusion.
Makes
Uh,
sense to me. I think so.
oh, you think so too? What were you
Yeah,
going to say, John?
I'm just following all the numbers.
Gotcha. Okay. So yeah, this is again that higgledy-piggledy way of doing it, but it does work. It's just this is not one that lends itself easily to Kirchhoff's loop rule and Kirchhoff's junction rule. You could use it, but it's not necessarily that helpful. So what I'm going to do now is I'm going to calculate V4. So what we see is V4 using Ohm's law. I don't know why I have this obsession about writing neatly, but I just can't write that crap like that. The current through the 4 ohm resistor is 0.5129 amps. And of course, it's going through a 4.00 ohm resistor. So I'm going to take that and multiply it by 4, and that gives me 2.051 volts. And again, that's one extra sig fig than is correct. So I'm underlining it just to keep track. And then I covered up the underline with the red mark because, that just makes it so much more helpful. Okay, so now we got V4. Now, the left-hand side of the 4 ohm resistor has a voltage of 11.5 volts. So I can do 11.5 volts minus 2.051 volts. And that would give me 9.449 volts. So that actually is the voltage on the right-hand side of the 4 ohm resistor. So I'm going to write in here 9.449. I'm going to put it in a bubble like I do. And I'm going to say it's this dot, it's this dot, and it's this dot. So what that tells us is the right-hand side of the 5 and 6 ohm resistors are 8.048 volts, and the left-hand sides are 9.449 volts. So I can just do a subtraction, and that'll get me the voltage across the 4 ohm and the 5 ohm, or excuse me, the 5 ohm and the 6 ohm resistor. So doing that, I'm going to say V5 equals V6, which equals 9.449 volts minus 8.048 volts is equal to, so I'm going to do minus 8.048, and that gives me 1.401 volts is equal to V5, and that's equal to V6. So I'll box it off in red again. Everybody agree with everything I did there? All right, because of that, I can get the current through I5 by just saying V5 is, or excuse me, just saying V5 is equal to I5 times 5. So let's do that. And rather than do that for the 6, I'm going to use conservation of charge. So we can see both things in action here. So I'm going to say 1.401 volts is equal to, notice that's V5, that's equal to I5 times, and I don't think I had calculated I5 yet. No, I hadn't, times 5.00 ohms. So that gives me that I5 is equal to 1.401 divided by 5 gives me 0.2801. So that's 0.2801 amps, and that's equal to I5. So at this point, I could do exactly the same thing with I6, but instead I'm going to choose to use conservation of charge because I know I4 breaks up into the current through I5. So for instance, I know I4, actually let's write it in purple. I know I4 is equal to I5 plus I6. So I can say I6 is equal to I4 minus I5. So with that, I say I6 is equal to 1.401 minus, oops, that's not the right one. Glad I caught that. It's equal to I4. Where did I put I4 now? Oh, there it is. 0.5129 minus, that was I4, minus I5. And where did I put? Oh, there it is. 0.2801. So I did 0.5129 minus 0.2801. That gave me 0.2328 amps. Okay. So that is the answer for the current through resistor 6. Of course, I could have also done the other way. So let's just check that just to make sure our work is right. We found that the voltage across 6 was 1.401. I'll call this a check. I found that that's 1.401 volts. That's equal to I6 times 6.00 ohms. So I6 in this case is supposed to be equal to 1.401 divided by 6, which gives me 0.2335. 0.2335. So notice it's accurate to the actual sig figs, i.e. the 233, but not accurate beyond that, which is exactly what we expect. So that's a check. And that's it. We've now done everything that we could possibly do with this. You could go back and check things like the voltages we did using Ohm's law. We could check and see if it works according to current laws and stuff like that. But this is sufficient. So anybody have any questions on that one? So you can see it's kind of fun. I like it. It's like a little puzzle trying to figure out what all the pieces are. So I highly recommend doing that kind of stuff. It'll definitely help you. But it looks like we don't have any real questions on it. So I'm going to try to, I just noticed my chat window went away. So I'll put the chat window back up. All right, I got that up. Now we're going to go on to another problem. So after that section and the Kirchhoff's loop rule and Kirchhoff's junction rule that we covered at the end of last class, I do recommend you look at more of those. So just go to my YouTube channel and do Kirchhoff's loop rule, or just do a search for Kirchhoff and ignore ones that have NAS in it, because that's from my astronomy class, and Kirchhoff has entirely different rules that he used in astronomy or that he developed for astrophysics and astronomy. So if you see any ones that have the course as a NAS course instead of a PHY course, then that's not your huckleberry. So definitely check that out. So there's a couple of those. I think I even have a couple linked in our Canvas course. But if I don't, like I said, definitely check it out there, or just look for other ones, because the more practice you have with solving circuits, the better off you'll be. That is another thing, like the 3-step process, which could appear on this next face-to-face exam, using Gauss's law or Coulomb's law to find the electric field, then using V equals a negative integral at E dot dl to calculate the voltage difference between two parts, and then using C equals Q over V to calculate the capacitance. That's not going away. So that is something that might appear on this next face-to-face exam and might appear again on the final exam. So make sure you guys figure out how to do that stuff. Additionally, solving the systems of equations for loop rules and junction rules to solve circuits, that's sort of a required skill set. So make sure you get that worked out. Of course, that's chapter 26, and that's not on this test, but the other one could be. All right, so the next section we're going into is basically what we call an RC circuit, not the RC that you're familiar with, which means radio control. This is the RC, meaning resistor capacitance circuit. So I've got a picture of a typical RC circuit. You see I have a battery which has a EMF E. Remember, that's just the old terminology that we use, but it's supposed to be voltage. So we've got that battery. It's connected to a resistor and then to a capacitor in series. And then there's a switch, and you can throw the switch at any instant. If you apply Kirchhoff's loop rule, you get E minus IR minus Q over C equals 0. And then you let I be dq dt, and that gets you a differential equation, which your book and your textbook author goes ahead and solves. The results are the equations listed above, so you need to have those on your equation sheet and know how to use them. So my equation sheet, remember, we don't require you to bring an equation sheet anymore. I actually have it on there, but these equations will be on there. Okay, now I'm going to show you how to use them. What you want to see, though, just for the record, these top two, the Q and the V, if you actually plotted them versus T, this would be either Q or V. What you'd see is that the charge or the actual voltage across the capacitor will asymptotically approach a value. In the case of the charge, it would be CE. But in the case of the voltage, it would just be E. Okay, so that's what that graph looks like. And then, of course, if you did the graph of the current versus time, it would be basically like this. And that value right there is E over R. And it drops by basically 37% after one time constant. The time constant is RC. The other one grows by 63% after one time constant. So you can use that and just realize these guys point to 63%, and this one points to 37%. So hopefully that'll be enough for you to understand what's going on here. So in example 2, I say, consider the circuit above with C equals 0.60 microfarads and R equals 10. That's supposed to be a 10 dot, but my dot got hidden by the T. A 10.0 kilo ohm, and the EMF is 24 volts. So for part A, they want to know what is the time constant, and that's the tau, which is defined to be R times C. It's a good practice for you guys to convince yourself that R, which is in farads, and R, which is in ohms, and C, which is in farads, when you multiply them, you get units of seconds. So do that at some time. It might be helpful to you, but here's the solution. Now, this one, I actually have the equations written above, so I'm not going to take time to do that. But tau is equal to R times C, which is going to be 10.0 kilo ohms times 0.60 microfarad. Now, a micro times a kilo gets a milli. And if you multiply 10 times 6, you get, or 10 times 0.6, you get 6. So this is just going to be 6.00 milliseconds. Hopefully that makes sense to everyone. That's your time constant, like that. Now part B, they're asking for what is the maximum charge Q max the capacitor can have. Well, looking at the equation and knowing how those graphs behave, we know that Q max is actually equal to C times E, which I call Q0 in the little purple. That's because your book does it. But the main thing is this is the quantity. So I'm going to take the 0.60 microfarads and I'm going to multiply it by the 24.0 volts. And of course, that's going to give me micro. If I actually multiply 24 by 0.6, that's the same thing as multiplying 2.4 times 6. 2 times 6 is 12, and 0.4 times 6 is 2.4. So 12 plus 2.4 should be 14.4. And that should be micro coulombs is equal to Q max. Please check me on my arithmetic. I'm trying to conserve time by doing as much of the math in my head as possible, but I'm definitely prone to making some really crazy errors. So let me know if I screw up. That'll be helpful. I think Micah's here. He usually keeps me honest. I'm certain other people can too, not to disparage anyone. All right, so C, how long does it take to reach 99% of Qmax? So this is a question about what is the charge. And notice the Q of T is given, and they want to know at what time is this 99% of Qmax. So the way we work this one is as follows. This is part C. I'm going to write 0.99 because that's what 99% means. 0.99 of CE, because that's Q max, is equal to CE times 1 minus e to the negative t over RC. You can immediately see that the CEs cancel out, and you can also see that e to the negative t over RC can be brought to the left-hand side where it'll become positive, and the 0.99 can be brought to the right-hand side where it will become negative, and you have 1 minus 0.99 is 0.01. Now I can take the natural log of both sides, and that's going to give me negative t over RC times the natural log of e, making use of a logarithm rule that basically says the logarithm of x to the m is m times the logarithm of x. And that's going to be equal to the natural log of 0.01, which, by the way, is 1 over 100. Hey there, baby. Cute little guy. Actually, I shouldn't say guy or girl because I know how babies are. All right, so we can change this len of 0.01 to the len of 10 if we multiply it by -1, and then I have, in fact, no more negatives. So now I can see from this that t, which is what we're looking for, is actually equal to the len of 10 times RC, but RC is just the time constant, so we know that's 6.00 milliseconds. So if I take the len of 10, I get 2.302, and now I'm going to multiply that by 6, and that's going to give me 13.82. milliseconds. Carrying one extra sig fig is t, and I'll call that t to 0. Well, actually, I'll call it t to 99%. Okay. So notice, as I told you before, it's going to get about 63% after one time constant. 63% is quite a bit smaller than 99%. So you would expect this to be more than one time constant. And in fact, it looks like it's actually about 2.3 time constants. Okay. So that's part C. Does anybody have any questions on that one? All right. So a lot of the stuff is, when I cover the derivations, I think students get a little confused as to what's most important. So I'm trying to show you that these are supposed to be like plug and chug problems. If you go later and become an electrical engineer, then probably being able to solve those differential equations might become more important. But right now, your duty is just to figure out how to apply the equations that I've managed to derive for you, except for the ones where I explicitly say the derivation is required, like in the derivation of capacitance that I was just talking about. So let's look at answer D now. So for part D, they want to know what is the current I when the capacitor reaches 80% or 0.80 of Q max. So what we're going to do is find the time at which the capacitor reaches 0.80 Q max, and then calculate I with the other equation. So what I'll do is I'll say 0.80 CE is equal to CE times 1 minus e to the negative t over RC. And you can see what's going to happen. We're basically going to get negative t over RC times the ln of e, which is just 1, is equal to the natural log of 1 minus 0.8, which would be 0.20. And of course, that's you can interpret that to be 1 over 5, and you could make it the negative of the ln of 5. That would be fine as well. And from this, we're going to get t is equal to 6.00 milliseconds times the ln of 5. Again, remember, ln of 0.2 is equal to the ln of 1/5, which equals the negative ln of 5. That's how I'm doing all that. So the time that they asked us for, which is not the whole answer, by the way, is ln 5, which is 1.609 times the 6 milliseconds. So this is going to be 9.657 milliseconds, which I can say is also 1.609 tau. Okay, now that's not really what they asked us, but I'll underline it with red just so we'll know where it came from. But now I got to use that to calculate what the current would be. So I of 9.657 is supposed to be equal to, I'm going to take the 24 volts and divide it by the 10 kilo ohms. So 24 divided by 10 just gives me 2.4, but when you're dividing by kilo, that makes milli. So I'm going to call this 2.4 milliamps times e to the negative 1.609 tau over tau, which is just a lot easier way of calculating it. So I'm going to say E, which is normally the inverse of the ln. I'm going to say e to the negative 1.609, and that gives me 0.20000, which is sort of what you expected. And now I got to multiply that by 2, by 2.4. I'm going to write this here. So times 2.4, that gives me 0.48. And this should be 4802 milliamps. And that's equal to, well, I'll just box it off this way. What the heck? That's equal to Nelly. That's equal to I of 9.657 milliseconds. Any questions on that one? So pretty straightforward, hopefully. It's just, basically learning all the symbols and understanding where things go and what they mean. Let's look at part E now. I feel like I'm sort of flying through this, so please, if you're not getting something, make sure you ask me. E, what is the maximum current? So if you look at the graph, the purple graph that I did on the far right-hand side up at the top, you'll see the maximum occurs at t equals 0. At t equals 0, e to the negative t becomes 1. So it's just e over r. In fact, that's, sort of what you expect is, in some sense, it's almost like all the voltage is going to try to exist across the resistor as if the capacitor is not there at all. But slowly, all that voltage is actually going to go across the capacitance, while the voltage across the resistor slowly drops down to 0. So we're going to do this and say I max is equal to E over R, which is what we calculated before, is 24.0 volts divided by 10.0 kilo ohms. And of course, a volt divided by a kilo is a milli. So this is going to make a milli ohm, or excuse me, a milliamp. And we know it's 2.400 milliamps. So that's the maximum current. And I'll write that as equals I max. Any questions on that one? All right. Do notice that basically when the Q was 80% Q max, the current was 0.2 of I max. Okay, that's not happenstance. You might even try to figure out what that means for part F, but that's sort of the physics behind this. Okay, that's sort of some of the fundamental concepts behind it. So let's go ahead and start with part F. Maybe you can take that little tidbit of advice I gave you and see what you think. See if you can actually predict this answer. So what we want to know is what is the charge Q on the capacitor when the current is 0.30 I max. So I'm going to solve for time first and then plug it into Q, just like I did the other one, only in the reverse as what I did last time. So I'm going to say 0.30 times I max, of course, is E over R, is equal to E over R times E to the negative T over RC. And that's what I want to solve for the time. Okay. So I think you can see that we're going to get the natural log of 0.30, which is 3/10. So basically you could make that a negative ln of 3.33333 if you wanted, and that would work. But when I take the ln of the other side, I'm going to get negative T over RC times the ln of E, which we know is 1. So finally, I can say that the T is going to be equal to the ln of, I'm actually just going to write it in here. I'm going to do the ln of 10 divided by 3. And that gives me 1.204 times RC, which is our time constant. So that's times, well, let me write this to help people understand what I'm saying here. This is negative 1.204. If I did the ln of 10 thirds, that would be positive 1.204. That's the math that I keep using. So I just want to make sure y'all knew where that was going. So I'm multiplying 1.204 times the 6 milliseconds. And that gives me 7.224. Oops. 7.224 milliseconds. But again, that's not what we're asked to solve for. So I'm just going to underline it rather than box it off. Now I've got to plug that in for the Q so I can find out what the Q at that time would be. So in this case, I'm going to say Q of 7.224 milliseconds is equal to CE, which is really Q max. We know Q max is 14. Whoa, Nelly. I'm really getting aggravated with this. So it's 14.40 microcoulombs times 1 minus E to the negative 7.224 milliseconds over 6.00 milliseconds. That time I went ahead and wrote it out in all its details. So I get, I'm going to take 7.22, I'm going 7.224, I'm going to multiply that by -1. And now I'm going to divide that by 6.00. That's 1.204. Now I'm going to raise e to that power. So I'm going to say second function ln. And now I'm going to pull my answer. And that gives me 0.3. And then I've got to subtract 0.3, which is what this is. So let me write this down. I'm going to subtract that from 1, which would give me 0.7 times 14.4. And that gives me 10.08. Whoa, no. Oops, that's supposed to be 10.08, not 10.80. 10.08 microcoulombs is the answer. And that is Q for what did we do? It was 30% of Imax. I equals 30% Imax. Like that. So notice we did end up getting 70% of the charge when we were talking about 30% of the current. Just like we got 20% when we were talking about 80%, and we got 1% when we were talking about 99%, even though I didn't do that calculation. Anybody have any questions on that? So that's it. That's charging a capacitor. Okay. Now, just to explain what goes on there, because we don't have too terribly much time, but to explain what's going on there is when you first throw that switch, the electrons are, well, pretend conventional current. Basically, the positive side of the battery compels positive charges to run from it. They're going to go through the R, and in fact, initially, that just looks like a dead end. So all the voltage is going to be across the resistance R. That's why you see basically the current being E over R. And slowly, that's going to cause positive charges to reach the top plate of the capacitor in this drawing. And those positive charges are going to compel positive charges to run away on the bottom plate. So the positive charges are going to leave the bottom plate and head back through the closed switch and back into the battery. And that's going to continue happening until the voltage across the capacitance reaches the voltage of the battery, which is 24 volts. All right, let's quickly do, I actually left a separate page just in case that needed more pages. So let's quickly do the discharging a capacitor. So discharging a capacitor is a little different, but it starts off with Kirchhoff's loop rule, but this time we don't have a battery in there. We just have Q over C minus IR is equal to 0. But this time, because the current that we're measuring comes at the expense of the charge on the capacitor, I is actually negative dq dt. Then when we solve that differential equation, we get these three nearly identical solutions. And now we can apply this for this problem. So here's our solution. Notice the problem says Consider the circuit shown with E equals 15.0 volts. By the way, I've got a different circuit off to the left. That's the key point here. Okay, so the electromotive force is 15 volts. That's what the battery is. The capacitance is 5 microfarads, and they didn't give us R. It says we know that the current decreases to 60% of its initial value after 30.0 microseconds after the switch is thrown from point A to point B. So we're assuming that when the switch is thrown from A to B, that's our T equals 0. A, what is the initial charge at T equals 0 when the switch is thrown? And B, what is R? And finally, C, what are Q and VC at 50 microseconds? So what we have here is basically a discharging capacitor, and we're saying that the current decreases to 60% of its initial value. So to do that, I'm going to say 0.60 of I0 is equal to I0. Notice I didn't take the time to write Q0 over RC. We just know that's I0. I'll write it right here. So that's just I0 times e to the negative t over RC. That allows me to divide out the 0, and I can take the natural log of both sides. That's going to give me the natural log of 0.60 is equal to negative t over RC. And that actually just gives us the amount of time. But luckily, we know that amount of time is 30 microseconds. So I can say, oh, I should go ahead and write ln E here just in case anybody didn't understand. But I'm going to say that's equal to negative, not 60, 30. Negative 30.0 microseconds over RC. Okay. So now I can say ln of 0.6 is equal to negative 0.5108. So 0.5108 is equal to 30.0 microseconds over R times C, which we said was 5.00 microfarads. So those actually cancel out. And from this, we can solve for R. And R looks like it's going to be 30 divided by, let's just say it, 30.0 seconds divided by 0.5108 with no units times 5.00 farads, because remember the mu's actually canceled out. So I'm going to do 30 divided by parentheses the answer times 5, and that gives me 11.75. And that's 11.75 ohms with 1 extra sig fig. So we've now figured out the resistance is 11.75 ohms. Any questions on that one? All right, now part B. That was part B, actually. What is the initial charge at T equals 0? Oops, I forgot that. What is the initial charge at T equals 0? So this was actually part B. I don't know why I did it first. I may be suffering from dementia. So here's A. A is what is the initial charge at T equals 0? So the initial charge, Q0, I don't show it there, but basically what you know it would be is, oh, because this one had a 15 ohm, or excuse me, a 15 volt capacitor, or excuse me, a 15 volt battery, we know that capacitance C is equal to QV, Q over V. C is equal to Q over V. So that means Q0 is actually equal to C times V, which is the battery voltage. And the C we know is 5.00 microfarad. and the voltage is 15.0 volts. So we should get 15 times 5 is 75. And that's 75.00 microcoulombs equals Q0. So that's the initial charge. All right. Now we can do part C. Part C says, what are Q and VC at 50 microseconds? So Q of 50.0 microseconds is clearly equal to 75.00 microcoulombs times e to the negative 50.0 microseconds over RC, and R is 11.75 ohms, and C is 5.00 microfarads. So you see again, the micros cancel out. So what I'm going to do is I'm going to say negative 50 divided by parenthesis 11.75 times 5, close parenthesis. That's negative 0.8511. And now I'm going to raise e to that power. So I'm raising e to the negative 0.8511 power. That gives me 75.00 microcoulombs times 0.4270, like that. So I multiply this number times 75, and that extra zero was not a sig fig. So that gives me 32.02. So I say Q of 50.0 microseconds is actually equal to 32.02 microcoulombs. We can do the exact same thing for V. And when we do that, we're going to get VC of 50.0 microseconds is again equal to, in this case, we've got the initial voltage, which is basically the Q0 divided by C. So we know that's the 15.0 volts times 0.4270, because we know that's the same value. So 0.4270 times 15 gives me 6.405 volts. And that's equal to the voltage across the capacitor. Any questions on that? All right. Again, I left an extra space for that one. The last two things I wanted to cover is how to use a galvanometer to make a ammeter, and then how to use a galvanometer to make a voltmeter. So let's just start right into this because we don't have much time. I only got like 8 minutes. So the trick with this is you have a galvanometer, which is basically what we use in that mapping electric fields, that little thing that we kept making read zero so we could find the little dots to connect the points on the equal potential lines. That was a galvanometer. And you notice it only went up to like 50 microamps, something really, really small. So it's not it doesn't have a very wide range, and it's actually a simple mechanical device that basically just has a magnet and a loop of wire that tends to align itself closer and closer to the magnet depending on which way the current going through the loop of wire is. But it's so simple, you can just use it and go with it. The only problem is it can only handle so much current. So what we do in this case is remember that when you have something in parallel, the current chooses the lion's share of the current to be in the smaller resistance, and the smaller current to be in the larger resistance. So what we need to do is create a alternate path. It's called a shunt resistance for the actual current. So in this case, we're wanting to do 1.00 amps. and this thing only takes up to 20 amps, so, or 20 microamps. So 1.000000000 amps is what we're wanting to get. But what we have is microamps. We have 20.0 microamps, which is basically 0.000. That gives 1, 2, 3, 4, and then 20 amps like that. So I'm going to put 0.00020, and I just went on a rampage there, putting all those zeros in just to make sure I had enough. Okay, now I'm going to subtract that. Now, luckily, this is enough for my calculator to actually do it, but normally I would take the time to do that digit by digit, because sometimes you have such a small amount, you have to do it by hand. So I'm going to do 1 minus or let's say 1 minus 20 e to the negative 6. That gives me 0.99998. So this is 0.99998, which is exactly what we expect. So that's the amount of current that goes through the shunt resistance. And the word I'm using is SHUNT. So what I'm going to do is imagine this with my galvanometer. So you can picture, and hopefully y'all will get this little reference. Okay, and this guy right here has a resistance that is in fact 25.0 ohms. Okay, so these two dots are going to be the input, and the output are the COM and the V omega ports of the galvanometer. Well, of the ammeter that we're making. Now, what we have to do is provide an alternate path for the lion's share of the current, and that alternate path is going to be this. This is going to be our shunt, and all we have to do now that I've drawn this out is just calculate that R shunt, and we'll be done. Okay, so what I know is 0.000020 amps is going through there, and what's going through here is 0.99998 amps is going that way. They're in parallel though, so V shunt has got to equal V galvanometer. And of course, Ohm's law tells us that V shunt is I times R shunt. So I'll say 0.99998 amps times R shunt is equal to 0.000020 amps times 25.0 ohms. Sorry, this is supposed to go up in there. Okay, so if I take this 0.000020 times 25, I get 5 times 10 to the negative fourth. Now if I divide that by 0.99998, that gives me 5.0001. So R shunt is equal to 5.0001 times 10 to the negative fourth ohms. Now that's a really, really small resistor. The trick to that is using a really low resistor and then put a bunch of them in parallel so that you keep making it smaller and smaller. But if you do, and you can ignore that 0.001, but basically that's it. You just need to create an equivalent resistance to about 5 times 10 to the negative fourth ohms, and that will give you the actual the actual ammeter that you want. Any questions on that one? Well, the other problem was supposed to do this. I'll just tell you quickly. The way this is supposed to work is you're supposed to have basically a resistance that you put in series with the galvanometer. And of course, the galvanometer specifies a resistance and a current, so you actually know what the maximum voltage is for the galvanometer. It's what do we say, 20 microamps. So 20 microamps times 25 ohms gives me 500 microvolts. So this quantity from here to here is 500 microvolts. What we need, though, is the whole voltage from here to here. We need that whole thing to be 50 volts. So all that's left really is to find a way to calculate a resistance R that gives you the remaining voltage from 50 volts to 500 microvolts, which is, by the way, 0.500 millivolts. So that's basically it. I think y'all can probably figure out from there how to do it, but that's it, everybody. You're free to go. I will actually write the answers on this. I'll do the calculation really quickly and I'll put it on the document. So when I post it in my Google Docs, you'll actually have the answer there. But I suspect you guys can fill that out already. I'm going to wait for the last person to leave, and in case anybody has any questions, so you're free to go. Thank you, everybody. Don't forget to type in your name first and last in the chat before you split. Anyone? Anyone? So that's what our voltage has to be. So we're going to say 49.9995 volts is equal to the current going through it, which has to be the very maximum, which is 20 microamps. Times R. So R is going to be 49.9995 divided by 20 e to the negative 6. And that gives me that gives me a big one, 2.49 million. So 2,499,975 ohms is the real answer there. So hopefully that makes some sense to you guys. Looks like Richard's still here. You got a question for me, Richard? All right. Well, I'm going to go ahead and split. It doesn't look like maybe he's not even here. Have a good day, everyone. Thank you for coming. Bye-bye.